Hi everyone. We're going to get started with Calculus 3. This is for the June session in 2020, if you're in my class. And we're going to hit some of the highlights of what you'll want to do before the class starts on this page, and then we'll actually get into the course itself. So to begin with, make sure you check out your Canvas page. It'll have all sorts of things there like your syllabus and a calendar for due dates. And then also it'll have a link to WebAssign, which is where all of your assignments will be. This is where your homework, your test, your quizzes, all of those type of assignments will be on WebAssign. So if you're used to this from Cal 1 or Cal 2 at Mississippi State, this will flow straight into it. You probably won't even have to buy a new access code or anything. It should go straight in there. So check out Canvas. Also, you'll notice there'll be some blank notes and some worked notes that will be on Canvas. That will be the notes that I'm going through here that you can follow along if you want to write them out yourself or if you want to look at what's going on as I go through them. Either one is perfectly okay. And then all these links for these videos will also be on YouTube as well, and on Canvas. So they'll be in both spots. So the notes will be there if you want to follow along with what I'm doing. Besides that, what else is on Canvas? Well, that's about all I can think of at the moment. So let's go ahead and start with what we're going to talk about in Cal 3. Calculus 3 goes through chapters 10 through 13. If you have the actual book, we're going to cover almost the entire chapter of each one of those, except for chapter 12. We don't hit every single section in chapter 12. And if you have any questions, feel free to email me. My email is bannick@math.msstate.edu. If you have any questions, feel free to contact me. Also, my office hours are on Canvas as well, so that's one other thing that's on the Canvas site. The syllabus, which also includes my office hours. Those are 9 a.m. Monday, Wednesday, and Friday. So if you have any questions, let me know. So let's start with Cal 3. Cal 3 starts with 10.1, which is parametric curves, or curves defined by parametric equations. And so what is that? Well, imagine that you have a particle that moves along a curve, and it's wobbling and wibbling all over the place, so it's not going in a very good line, and it ends up being impossible to describe that curve using our notation from what you would see back in Cal 1 or Cal 2, where y is a function of x. So we can't do that here, mainly because it's going to do things like fail the vertical line test. But we could write our functions instead of y equals f of x, we could write our x value in terms of a function of t and our y value as another function of t. The t will tell you when you are at a spot. The x and the y tell you where you are at that spot. So your t is kind of like your time component. After a certain amount of time, your x is here and your y is there. And then the x and the y tell you where you're actually at. So you might end up with a curve that looks kind of crazy like this one down at the bottom of the page here. That's a parametric curve. Definitely not a function in terms of a vertical line test type things from Cal 1 or Cal 2. So we got to figure a way how to actually draw these things, and that's what this section is about. So, for instance, sketching a curve. We're going to do this very much like we would have done if you were doing something in algebra, beginning algebra. We could do something like plot points. So that's what we're going to do. I'm going to have a table over here on the right-hand side from -3 to 3 on the t values. Those are my time components here. Don't think too much of the fact that the t is negative in terms of time. Don't worry about that much at the moment. But if it was a value of when something occurs, we're going to figure out where the something occurs for the x and the y. So for instance, you just plug in points. If I was to take x at -3 for the t, I just plug it in. I get -3 squared minus 3. That is 9 minus 3, or 6. So this first term is 6. And you just do that for every x value all the way down. When you'd have x is -2, you would have -2 squared, which is 4. 4 minus 3 is 1. If you plug in -1, you would have -1 squared minus 3. That's 1 minus 3, or -2. If you plugged in 0, 0 is really nice because 0 squared is just 0. Minus 3 is -3. And since this is actually an even function, if you plug in a positive or a negative of the same value, -2 and +2, you'll get the same output. And so in this case, you'll get the same x value. If you plug in 1, you'll get 1 squared minus 3, which again should be -2. If you plug in 2, you'll get 2 squared minus 3, which again is 1. That's a 1 there. And if you plugged in 3, you would again get 3 squared, which is 9, minus 3, which is 6. Now you have to do this twice now as opposed to what you would have done in algebra, because we're making the points x and y. We don't have any y values yet. So you have to do that again with the y's. You have to do what is y of -3. And do -3 plus 2, which is -1. If you plugged in -2, you get -2 plus 2, which is 0. And this is a linear function with a slope of 1, so we're only adding 2, shifting it over. And so all these numbers are only going to be off by 1 all the way down. If you plugged in -1, you get -1 plus 2, which is 1. And so on. If you plugged in 0, you get 0 plus 2, which is 2. And if you kept going, you'll notice there's a pattern. This is 3, this is 4, this is 5, and you can plug them all in if you want to. But our points are the points 6, -1, or 1, 0, or -2, 1. So all of these points, those are the points that I have to work with. And I'm going to plot those points on my graph. So the the positive 6, -1 would come about right here. 1, 0 is right here. -2, 1 would be about right there. -3, 2 would be about right here. The -2, 3 would be about right here. The 1, 4 would be about right there. And the 6, 5 would be probably somewhere in this area right here. What you might notice is this looks a lot like a sideways parabola. And you would not be wrong. Usually if you have one function of, like in this case, x has a squared term on it and the y has a linear term, that's usually going to be a parabola of some sort. Not necessarily to the right or to the left, but could be actually in any direction since it's parametric. Now one thing that's a little different with parametric equations is you get in the knack of putting arrows on the ends of the lines. If you're doing algebra, for instance, to let you know that the line keeps going up, basically. We can't do that here parametrically because we're going to have to put an arrow on there to tell you how time is moving through the graph. And so we don't want to put arrows on both ends of our graph here. So we want to figure out which way time is going and then add an arrow to show that. Our very first point, the negative, when t was -3, we started down here and we worked our way around to this point, this point, this point, this point, this point, and this point. So we're going from the bottom and around and then back up. So our time is moving this direction. So we need to put at least one arrow somewhere on that graph to let you know which way time is moving. Most of the time you'll see graphs have multiple arrows. So that is perfectly okay as well to put multiple arrows. We usually don't put any arrows on the ends. You can, if you really wanted to, put an arrow right here, but you could not put an arrow on the other end going the opposite direction. And so that's how you graph it. Not only do we want to graph it, but sometimes we would like to eliminate the parameter. So I'll show you that next. So this says eliminate the parameter. We have x equals t squared minus 3, and you have y equals t plus 2. So it does not matter, but you want to solve one of those equations for t and plug it into the other one. Solving the y would be a lot easier for t than it would be for the x because of the squared on the t squared. And so what I would do is just subtract the 2 from both sides and get that y minus 2 equals t. Then I could just take this, plug it in there on the x, and say that x equals y minus 2 squared minus 3. And I have eliminated the parameter. There's no longer a t in the problem. And this is a sideways parabola. Anytime you have an x equal to a y term that is squared, that's going to be a sideways parabola. Just like a up and down parabola like you're usually used to in Cal 1 or college algebra would have y equals an x squared on the other side. Okay, let's do another curve. Sketch the curve defined by x equals t squared and y equals t cubed. Again, I'm going to plot just a couple less points here, but the process is the same. I would want to plug in negative 2, negative 1, 0, 1, and 2 into both of them. So if I plug negative 2 into x, I'll get negative 2 squared, which is 4. If I plug in negative 1, I'll get negative 1 squared, which is 1. If I plug in 0, hopefully that's pretty obvious, that would be 0. If I plugged in 1, 1 squared is 1. Again, this is an even function, so you'll notice that whether or not if you plug in the negative 1 or the positive 1, you still get 1. Same way with the 2. If you plug in negative 2 or positive 2, since it is an even function, you'll get 4 either way. And then for the y's, I would have basically the same thing. If I plugged in y equals, or t equals negative 2, then y would be negative 2 cubed, which is negative 8. This is an odd function, so if you plug in a negative 2, you'll get negative 8. If you plugged in a positive 2, you'll get positive 8. And so if you plugged in the negative 1, you'll actually end up with negative 1, because negative 1 cubed is negative 1. If you plug in 0, again, 0 to pretty much any power is 0. Y of 1 would be 1 cubed, which is 1. And if you plugged in the 2, just like with the negative 2, you'll get an 8, except this time it's positive. And so here's our points. 4, negative 8, 1, negative 1, 0, 0, 1, 1, 4, 8. And I'm going to plot those points. So 4, negative 8 would be way down here. 1, negative 1 would be right here. 0, 0 is the origin. 1, 1 is right above that. And 4, 8 would be about right here. And you might say this kind of looks like a parabola as well. And it's not a parabola. We'll talk more about why it does this a little bit later in the next section. But it's more of a shape like this. So didn't connect my lines there. You might remember when you did Cal 1, you talked about concavity. We'll talk about how you know whether it's concave up or concave down in the next section. But this is very much like if you were to graph a function like x to the 2/3. This is very much like y to the 2/3. In fact, we'll see that when we eliminate the parameter. But if you're going to draw those arrows to let you know which way time is going, we started down here at the bottom and went up. We started at the bottom, went up through our points. That means our arrows have to follow that same pattern. We have to go from the bottom to the top. And so I would put arrows on it like that. And that would be my graph for this particular function. If I try to eliminate the parameter for those same functions, x equals t squared, y equals t cubed, you have to get the t by itself on one of them. And the easiest one would actually be the y. They both have powers on them, but if you take the square root on both sides for the x's, the square root could be positive or negative, and you'd have to put that plus and minus in there. If you did it for the y's, though, the cube root takes care of the negative and the positive for you. And so I'm going to solve this one by doing the cube root on both sides. So if I do the cube root of y and the cube root of t cubed, I'll end up with the cube root of y equals t. Or, if you wanted to, you could write it as y to the 1/3 equals t. Whichever one you want to do. They mean the same thing. But this t value would then have to come in up here and say that x equals the t would be y to the 1/3 or the cube root of y squared. So you'll get x equals y to the 2/3. And I have eliminated the parameter. And that would be my answer. Let's do one with trig in it. So here we're going to do sketch the curve defined by x equals sine 1/2 theta and y equals cosine 1/2 theta. And we're just going to plug in here, we're going to use values in multiples of pi for time because of the sine. And instead of a t, we actually have a theta in there. So if you would like, you could change this to a theta on the notes. So we're going to let theta be negative pi over 2, 0, pi over 2, and pi, and plug them in. Very much like what we've been doing. So if I plug in negative pi, I'll end up having sine of 1/2 of negative pi. That's actually the sine of negative pi over 2. Sine is an odd function, so if you plug in a negative, that negative could actually be factored out in front. Sine of pi over 2 is 1, so sine of negative pi over 2 is negative 1. If I was to plug in negative pi over 2, I would end up with sine of negative pi over 2 times 1/2 would be a negative pi over 4. And that would be negative root 2 over 2. By the way, if you're not extremely good with trig, or trig just basically makes your heart rate increase, you will want to know that all of chapter 10 has a good amount of trig in it, especially once we get into 10.3 and 10.4. So if you don't know a whole lot of trig, I would brush up on things like identities and plugging values in. Those pop up a lot coming up. So x at 0 would be just sine of 1/2 times 0, which is 0. Sine of 0 is 0. If you plug in pi over 2, you would get 1/2 times pi over 2, which would be pi over 4. That is root 2 over 2. Remember, sine is an odd function, so if you plug in a positive value, you'll get the same thing that you would if you plugged in the negative value, just with the opposite sign. And then if you plugged in the pi, you get 1/2 times pi, or pi over 2, which is 1. And then I want to do the same thing with cosine, or the y values. So y at negative pi, it's 1/2 times negative pi, just like it was on the sine. So I'll get cosine of negative pi over 2. Well, cosine is an even function, so the negative has no bearing. So whether it's negative pi over 2 or positive pi over 2, cosine of pi over 2, that is 0. If you plugged in negative pi over 2, you would actually end up being cosine negative pi over 4. Again, the negative doesn't actually matter. this would be root 2 over 2. If you plugged in 0, you would be at cosine of 0, which is 1. If you plugged in pi over 2, you would be at cosine pi over 4, which is root 2 over 2. Or if you plugged in pi, you would be at cosine pi over 2, which again is 0. So my points are negative 1, 0, these things with the root 2 over 2's, 0, 1, some more root 2 over 2's, and 1, 0. So my points would plot starting at negative 1, 0. Square root of 2 over 2 is about 0.7, a little bit more than 0.7. So if you go to about 0.7 and 0.7, maybe about right here. Then we have the point 0, 1, the 0.7 and 0.7 again, and then 1, 0. You actually end up, and don't get confused, this is not a parabola. This is actually a semicircle. You get the top half of a circle. Plotting points starting on the left-hand side, going around the circle to the right-hand side. So my arrows need to show that I'm going around the circle in a clockwise notation. Now you only get half a circle because we only went from negative pi to pi. But for instance, if I would have picked theta values to go from 0 to 2 pi, you actually get an entire circle here. And you can see that once it's eliminated, once we eliminate the parameter for the theta. So if I eliminate the parameter, this comes from an identity. So we have x equals sine 1/2 theta, and y equals cosine 1/2 theta. And we want to get rid of the theta. You might remember from a long time ago, you had an identity that said sine squared plus cosine squared equals 1. Now, what you may or may not remember is that it's sine squared of anything, any angle, plus cosine squared of that same angle is 1. So it could be theta, it could be 2 theta, it could be 3 theta, or in our case, it could be half a theta. And so since they are the same, they both have 1/2 theta in them, then if I was to square each one like this, uh-oh, I left the 1/2 off, didn't I? Oh no. Oh, I don't have an eraser, but what I do have is a white pen. So I'm going to take my white pen and kind of go like that. There we go. And put a 1/2 theta there. If I square it, this has to be 1. But sine squared of 1/2 theta is actually the same thing as x squared. I'm just squaring sine 1/2 theta, which is x. And cosine squared of 1/2 theta is actually y squared, which equals 1. I have eliminated the parameter, and this, you might remember, is the equation, the standard form of an equation of a circle with a center at 0, 0 and a radius of 1, which is actually what our graph was showing us on the previous slide. Okay, let's do one with values that don't come out nice. So here we're going to sketch e to the negative t plus t is my x, and e to the positive t minus t is my y. These values you'll have to have a calculator for to come up with the decimal approximations, and we will need decimals if we're going to graph them, unless you know what things like t squared minus 2 is. But anyway, so we're going to start with the x's. So x at negative 2. That would be e to the negative 2 would make a positive 2 minus 2. And that's about as good as you can get. This is e squared minus 2. If you plug a, not a y in, but if we were to plug a x at negative 1 in, I would have e to the negative negative 1, which is positive 1, minus 1, which is just e minus 1. That one I can do. E is 2.72-ish, so minus 1 would be 1.72-ish. So that one, I got that one down. If you plug in 0, I could do that one as well, because I'll get e to the 0 plus 0. That's just 1. If you plug in 1, you'll get e to the negative 1 plus 1, whatever that is. I'll have to pull a calculator out in a minute. I'll do that in just a moment to get our decimals. And if you plug in a 2, I'll have e to the negative 2 plus 2. Again, whatever that is. I'm going to do the same thing for the y's first, though. So if I plug in negative 2 in for the y, I'll get e to the negative 2, and then minus negative 2 would be plus 2. One nice thing here is what you'll notice, my y value at negative 2 and my x value at positive 2 actually end up being the same thing. So I don't have to type in a whole lot into the calculator. And it'll actually be the reverse of the column on the left as we work our way through it. If I do y equals negative 1, I'll have e to the negative 1 plus 1. If I do 0, I'll have e to the 0 minus 0, again, which is 1. If I plug in 1, I'll have e to the 1 minus 1, or just e minus 1, which is the 1.72 that I did up there. And if I did y of 2, that would be e squared minus 2. So there's my e squared minus 2. Now, if you type in the calculator, e squared minus 2, I'll end up with 5.39. And that'll be that one and this one. If I typed in, I already did the negative 1 on that one. Let's do e to the negative 1 plus 1. If I did e to the negative 1 plus 1, I get 1.37. So I end up 1.37 there and 1.37 there. And if I did e to the negative 2 plus 2, I end up with 2.14. 2.14. Now, a few of these points I can't really use because of the way I made my graph. This point is too big. The 5.39 would be off the page. And this point right here is actually too big as well. So I'm going to use the 3 in the middle. I'm going to go graph these 3 points. 1.72, 1.37, 1, 1, and the reverse of that. So the 1, 1 is really easy to plot. The 1.72 and the 1.37 would probably be about right here. The 1.37 and the 1.72 would probably be about right there. Again, you would need more detail than this to really understand how the concavity is changing and the slope is changing, and we'll get to that, I promise. That'll be in the next section. But this graph actually has a really sharp V right here. I kind of missed that point, so I'll make it a little bit bigger. And our points are going from the 1.72 to 1.37. We're starting with this point, and we're going around this way. So our arrows need to reflect that we're going to the left and then up. Very much a V shape here. And it would just kind of expand outward from there. Okay, we're not going to eliminate that one. So we're going to go on to this type of problem here. What if you didn't have the actual equations, but you had the graphs of each one of those? So here, this is my x of t, right here, graph. This is my y of t graph. And based on those two graphs, I can give you kind of a rough estimate of what I think the overall xy Cartesian graph would look like. Starting off, you could pull off a few points right here. This point right here is at the point when x is 1. When t is 0, x is 1. And you can make a little table like what we were just doing. When t is 0, x is 1. At that same point, when t is 0, y is 0. So I have a point of 1, 0, starting right there. There's my point, 1, 0. I can do another one right here. This would be 1/2. When t is 1/2, my x value is at 2. And when t is 1/2, my y value is at 0. That leaves me the point 2, 0. And if I do another one, when t is 1, I'll end up with this point when x is 1 and y is 0, which doesn't do me a whole lot of good because that's the same point I started with. So plotting points is not always going to give you the graph. Like in this case, what happens between these 2 points? That's going to really depend on how you can read the graph. So your graph for your x, if you're looking at this graph right here, looking at this graph for x, it goes up, it increases, and then it decreases, which means I am going this direction on the x's, but then I have to come back to the 1. So I have to go both directions. I have to go towards the 2, then I have to turn around and come back towards the 1. Now, at the same time that's going on, my y values are going, looking at this graph, they're going up, down, and up. So my y's have to go, from this point, they have to go up to 1, down to -1, and back up to, starting at 0, going up to 1, down to -1, and then back to 0. So I have to be able to relate that in a graph. And so what happens, oops, I actually erased part of my axis. I didn't know I could do that. If I can connect the line back. Close enough. So my graph's going to start at this point 1, 0. My x's have to go bigger, and my y's have to go bigger. So I have to go upwards. And my y's doesn't get any bigger than 1. So at 1, it's going to have to come back down to go through this point at 2, 0. That's my halfway point. But then my x's start getting smaller, so I have to go back towards the 1. But I'm still going smaller on the y's to -1. So I have to start going back the other direction on the x's, and then I loop back around to get back to that point, going in a clockwise notation. In your graph, that's a very ugly graph, but that's basically what it would look like. And hopefully that makes sense. I did put a graph on here. It kind of looks like this right here. I kind of drew over it, but that's what the actual graph looks like if you're doing it out. Let's do another one. Same idea. This is your x of t. This is your y of t. You can plot points if you want to. I have values like this is -2. I have a value of 0 in the middle and 2. So I could plot those points if you wanted to. So if your t was -2, 0, and 2, then your x and your y could be read off the graph. And maybe that would help us. Let's see. At -2, your x, it's kind of hard to read, but it would be down here. This would also be -2. And your y value at -2 appears to be 0. When you hit your origin at 0, your x is at 0, your y is at 2. And on your 2's, your x graph appears to be at 2, and your y graph appears to be back at 0. So we have these points you can work with. So -2, 0, 0, 2, and 2, 0. Now you might say, well, that could be a parabola or a semicircle or lots of different things. So this is where you really have to pay attention to how your slope's changing. Your x's, starting at -2, have to go up, then back down, and back up. So we have to go this direction for a little bit, turn back around, and then go back this direction again. That's what that says. So we have to go one direction, stop, turn around, go back the other direction, and come back. And you still have to hit all these points along the way, so keep that in mind. You still have to hit every one of these points. The y's say you just go basically up to 2 and then back down to 0. It's the x that's going to make this kind of a loopy thing. And so we're going to end up with a graph where I have to be increasing all the way around for the y's till you get to 2, and then it comes back down. So I have to increase up to the 2 in the middle, and then I loop back around. But the x's have to go up, have to get all the way over to 2 on the x-axis, and then loop back around. So you're going to end up with a graph that kind of does this. It has to go up until it gets to 2, and then it's got to loop back around to get through that point. And then your y's have to go down, but your x's are still going down for part of the way, and then it's got to, oops, that didn't really go down, did it? It was supposed to go down. Ah! I try to erase with the marker, it won't erase. So we have to go down here. See if I can't make this go down a little more. Ah! My drawings are not very good, I apologize. And we still got to get back to 2. And so our graph looks something like that. Like I said, I do have the actual graph on here. I might have drawn over it again. But there it is. It's kind of a looping thing all the way around. Mine is a little flatter than the actual one, but that's okay. My graph's a little bit bigger. Okay, let's try one more. Here are my x's. This is my x of t. This is my y of t. And let's see, can we make another table of t's, x's, and y's? Well, to begin with, it looks like -1 should probably be about right here. And so when my t values I'll use will be -1, 0, and 1. When t is -1, x looks to be at 1. That's this point right here. At 0, I'm at 0, and at 1, I'm back up to 1. On my y values, at -1, I am at 1. At 0, I am at 0. And at 1, this is probably -1. And so my points look like this. I'm at the point 1, 1, 0, 0, and 1, -1, which is over this way. In this case, this will actually be a parabola. Again, kind of like that first one we talked about. If you have one equation that's a parabola and one's a linear straight line equation, you'll end up with basically a parabola. In this case, a sideways parabola. Depending on how good your drawing ability is. It's got to be better than mine. Mine's pretty awful. So we're starting at the point 1, 1, and we're going down to 0, 0, and then around. So our graph would look something like that right there. Okay, two things that are in this section that we're not going to spend a whole lot of time on right now. We will mention circles more as we go throughout the semester. But circles, instead of using a Cartesian equation like x squared plus y squared equals r squared, we could rewrite it to be parametric equations. And so circles, kind of like that example that we did with the sine 1/2 theta and the cosine 1/2 theta, we could take a little bit of trig. Like, for instance, you might remember a long time ago from trig that cosine theta was x over r, and sine theta was y over r. And that was one of the definitions for sine and cosine. Well, we can use these definitions to find the equation of the circle. If you multiply by r on both of them, you'll get that r cosine theta equals x, and r sine theta equals y. Those would be centered at 0, 0. But if we shift anything left or right, or up or down, we'll change the center. And that's the circle that we have right here. It's been shifted over by the center HK. And so to encompass that, our H affects the X values. So we could say that X is actually the shift H plus the R cosine theta. And the Y is the shift for the K value being the Y value, plus R sine theta. And these are the equations of a circle parametrically. And then one other topic that's in this section that I'm probably going to spend hardly any time at all on is the cycloid. The cycloid is if you take a circle, so here's our circle right here. You take our circle with a center, and there's a point on the outside of the circle. As this rotates, as it's spinning around, that point on the outside makes this curve. And that curve is called your cycloid. You might notice that to make one complete rotation around from endpoint to endpoint, from here to here, that number should not be surprising. This is 2 pi. And then if the next one would be 4 pi and 6 pi. But the equations of those are given by these two functions right here. X equals r times theta minus sine theta, and y would be r times 1 minus cosine theta. Like I said, I'm not going to spend a whole lot of time on it, but just in case you ever run into it, that's the equations for your cycloid. And that's the end of section 10.1.